All right, section 2 is on series and summation notation. Notice the word sum in summation notation. We are going to be, a series is just when the terms of a sequence are added together. So you're still going to notice patterns. You're still going to notice sequences like you did in the first section. We're now just going to be taking those sequences and adding them together. So an example of a finite and an infinite series. Here's an example of a finite. Remember, finite means it has an end. So 1. Now instead of commas, we have plus signs. And because we're ending, there is no ... at the end, right? So 1 plus 5 plus 9 plus 13 plus 17. For an infinite series, an example of an infinite series, you might already notice a pattern in both of these, but an infinite has your ... at the end. Okay. We can find the sum of a finite series, and we call this sum a partial sum. It's the sum of a specified number of terms in a sequence. Okay. You can find partial sums. An infinite sequence, they do not have defined sums. So most of these examples we're going to have below, there's going to be what we call an upper limit and a lower limit, meaning we're going to have partial sums for a specific sequence, okay? So these are going to be finite series. I just want to show you what this summation notation represents, what you're going to see down below. So let's put an example of one here. It's this Greek symbol, which stands for sigma, and it means the sum in math. Below, you're going to have n equaling some number, and then up above, you're just going to have another number up top. And then you're going to have your rule here off to the side. So I don't know, maybe 3n plus 1, just a linear rule. Okay. So this right here, this is the explicit rule for the sequence. And then this at the bottom, this is what we call your lower limit. It's where the series starts. And this would be your upper limit. All right. So if we were to write the above, the two series above in sigma notation, let's do the finite series first. We're almost always going to start with a lower limit of 1. Our upper limit would be however many terms we have here, so 1, 2, 3, 4, and 5, so going up to a limit of 5. And then hopefully you can see the rule, or the sequence here is just plus 4, plus 4, plus 4, plus 4. And we talked about writing explicit rules back in 9.1. This would just be 4 times n minus 1 plus 1. You could also just go back to term 0, which would be subtracting 4, and you would be at negative 3. So you could also have a rule of 4n minus 3. But now hopefully you can see when you plug in your lower limit of 1 into your rule, you get this first term of 1, right? 4 times 1 minus 3 is 1. When you plug in 2 to this rule, 4 times 2 is 8. 8 minus 3 is 5. You get your second term in this series, right? Let's do our sigma notation over here. This one goes on forever, so we're not going to have an upper limit. So we'll have our infinity sign up above. and then a lower limit of 1. And hopefully you notice for your rule, this is just 1 squared, 2 squared, 3 squared, 4 squared, so on and so forth. So this would just be n squared, quadratic rule. All right, some examples down here. Let's take these series that are written in sigma notation, expand them, meaning write them out like you have right here, and then evaluate. Find the actual sum. Okay, so for this first one, our lower limit's not 1 here, it's going to be 3, so we're going to start with 3. Plug that in, we'd have 1 to the power of 2 cubed over plus 1 over 2 to the 4th, plus 1 over 2 to the 5th, and finally plus 1 over 2 to the 6th, your upper limit. So we're adding 1/8 plus 1/64 plus, 1/64 would be at the end, plus 1/16, 1/32, 1/64. So that means our LCD is going to be 64. All of those denominators go into 64. This way we don't need to use a calculator. That would be 8 times 8, so we get 8, 16 times 4, so 4, 32 doubled, and then our 1. Add these all together, and we get 15 over 64 for this sigma notation. Remember, it's finding the sum. You're evaluating, you're finding the sum from a given lower limit to an upper limit with a specific rule. All right, let's try number 2, and then we'll let you try these next 4 on your own. Number 2, the rule is just 6. So from the 4th term all the way up to the 10th term, which is a total of, that's actually 7 terms, it's going to be 6. 6 plus 6 plus 6 plus 6 plus 6 plus 6, and one more, plus 6 gets us 42. Okay. So I know it's from the difference of the upper limit and the lower limit is 6. Sorry for all the 6's here. But that's actually 7 terms, right? 4, 5, 6, 7, 8, 9, 10. So maybe let's just make a little note down here at the bottom that the number of terms in a series is the upper limit minus the lower limit plus 1. Okay, just a good reminder to check. So if we looked at that first example, 6 minus 3 is 3, plus 1 is 4, and there's 1, 2, 3, 4 terms in that series. Okay, why don't you try 3, 4, 5, and 6 on your own. Expand the series and evaluate. Go ahead. Number 3, this should have been 9 plus 6 plus 1 minus 4, which gets you a sum of positive 12. For number 4, this should have been just 1 plus 2 plus 3 plus all the way up to 8, which would get you a sum of 36. Number 5 should have been negative 10 minus 12 minus 14 minus 16 to get you a sum of negative 52. And then 6, we had this example up above, 1 plus 4 plus 9 plus all the way out to 144. I guess the sum of 650. Okay. Hopefully you notice it can sometimes be a pain when you have lower limits and upper limits that are really far apart and you got to add all these together. Well, there's going to be some formulas that we're going to talk about next section that you can use when you have series that are really far apart and we want to find the sum of, say, 20 terms or 30 terms, something that you don't want to calculate by hand. And we'll talk about those next class. Okay. Now let's do the opposite. Now I'm going to give you a series, and I want us to write it in sigma notation. Okay. Well, first thing you should notice is what's the rule? We're going up by 3 here. It's 3, plus 3. And then we're almost always going to start with a lower limit of 1, n equals 1. We have a total of 1, 2, 3, 4, 5, so we're going all the way out to our upper limit of 5. And then our rule should just be 3n. You could do 3n minus 3, or you could just do, or sorry, just 3n is going to work here, because if you went back to term 0, you would be at 0. So just 3n works, and you have your rule right here. Let's try another one. Let's try number 2. This one's a little tricky because it's alternating plus, minus, plus, minus, plus, minus. If you just ignore that for now, you might notice that the denominator is just being doubled, right? These fractions are just being doubled. So starting at term 1, going all the way out to 6 terms, our first term would just be 1/2 to the power of n, right? If we plug in 1, we get 1/2. If we plug in 2, we get 1/4, 3, 1/8. And then a trick, if it's alternating positive, negative, is you could just multiply by whatever the term number is. Oops, sorry, not a negative n, just an n. You can just multiply, sorry, by a -1, right? But that would make the first term negative. We actually want the first term to be positive. So then we could just raise this to a power of n plus 1. And now that means, okay, second term's going to be negative, right? Because if we plug in a 2 here, we get 2 plus 1 is 3, and a negative raised to an odd exponent is going to stay negative. Then if we plug in, say, 3, we get -1 to the power of 4, which is going to become positive, and we have our 1/8 to the, or sorry, 1/2 to the power of 3, which gets us 1/8. And this checks out. Always a good idea to check and make sure your rule works. There's our rule in sigma notation. Okay, so you have another one where it's alternating negative, positive on number 4 and number 6. Just be careful, those two, the first term starting with a negative, not the second term. So you might need to change something up here in your exponent. All right, let's have you go ahead and try those next. We got a lot of examples there. Great, this one's also changing positive, negative. That's fine. Why don't you go ahead and try these next 6. They're quick. You're just writing the rule, starting with a lower limit of 1 and upper limit of how many terms, and we'll check to see your solutions when you are done. All right, go ahead, starting with number 3. Okay, number 3, starting at a lower limit of 1. There were 5 terms here. Hopefully you just had a rule of 4n plus 4. You could also have, actually, be careful here. If you're using the plus 4 at the beginning, you need your n minus 1 plus 4. There we go, that checks out. Or you could have done, starting at 1, going up to 5, and just having 4n. Either one of those rules work. Hopefully you can see why the plus 4 and just the 4n both check out. Okay, number 4, starting with a lower limit of 1, there were 6 terms. Our rule, just the denominator now, were those perfect squares. So 1 over n squared. Again, these are alternating negative, positive. So just multiply by -1. Now just to the power of n, because if you plug in 1, you're going to get your first term being negative. -1 to the power of 1 just stays negative. If you plug in 2 for your second term, -1 squared becomes positive, and you're going to be okay, and it's going to alternate positive, negative. How about for 5? Numerator is just staying as 2, and the denominator is all of your perfect squares, except we're starting with 4. So we had a lower limit of 1, 5 terms. Your numerator is going to be 2. Your denominator is your n squared, but we're starting at 4, not at 1. So I would just change this denominator to n plus 1 squared. And this works. You could have also started at a limit of 2 if you wanted and gone up to 6, right? And now you just have 2 over n squared. And now when you plug in 2, you would get your 4. Now your next term would be 3, and you would get 2 over 9. Both of those rules check out. Either one's fine. For 6, starting at a lower limit of 1, 6 terms. Your rule, it was just going up by 2, so we have just 2n. That's fine. However, we're alternating positive, negative, so you want to multiply by -1 to the power of n because the first term's negative. All right, last two here. Starting at 1, going all the way up to, well, there's 25 terms there, from 25 to 1. Great. And then it's just -1, -1, -1. Starting at, you could have started wherever you wanted. If you wanted to start at 26, then you could have just done 26 or -n plus 26. If you wanted to use 25, then your rule would have been, let's make that look a little neater. Up to 25. If you wanted to use the 25, you would need your -n times n minus 1. Sorry, just a -n minus 1 plus 25. Now when you plug in 1, you would get your -1, which becomes +1. If you plugged in 2, you would get your 1, but then -1, which is 24. So both work. It doesn't matter if you want to start with your first term or term 0. Okay. Last one. Starting at 1, going up to 6, there were 6 terms. Again, all of these numbers are perfect squares. Actually, it might have been easier if you just wanted to say, hey, I'm going to start this at 3, because that first term is 3 squared, and I'm going to go up to 4, 5, 6, 7, 8, and now you can just do n squared multiplied by -1. The second term is negative, then third term positive, then fourth term negative, so you need your n minus 1 up here. Other rule could be written as, if you wanted to start at 1 and go up to 6, you just needed n plus 2, because you weren't starting at n squared, you weren't starting at 1 squared, you were starting at 3 squared. So by plugging in the 1 there, you get your 3 squared with your -1 to the power of n minus 1. Okay, hopefully you noticed that there's multiple ways to write these rules. So if yours does not exactly match what I have on the key for the homework, that's okay. Just check to make sure yours works by taking any term number in the series. This would be term 4, plugging 4 into your rule and making sure it checks out, right? So I should get -36 when I plug in 4. 4 squared is 16. I'm sorry with this rule, sorry. I'm not plugging in 4 here because my lower limit is 3. Right? So that means this is term 3, 4, 5, and this is actually my 6. That's why I started with a lower limit of 3. So if you check with 6, you should get -36. 6 squared is 36 times -1 to the power of 6 minus 1, which is 5. So that's going to stay -1, and that checks out. Okay? So that's really the way you should check these rules. Again, we will introduce some formulas in these next 2 sections for when you are evaluating a series and you have a really large range of numbers, right? So say you want to evaluate for a series of 20 or 40. We have some formulas that we'll introduce next class. It's okay if your solutions don't match the key. You can always ask in class if they check out. All right, get started on the homework.